Okay. I hope everything is okay with the sound. So I would like today to describe a little bit more in details the argument by Shane and Uhlenbeck to prove the regularity, I mean the partial regularity, together with the dimensional bound on the singular set for minimizing maps. And if I have still a little bit of time, I will come back to this definition of harmonic maps with free boundary that I defined last time as well, and the last lecture tomorrow I will discuss various flows which are associated with these harmonic maps with free boundaries and what can we do with it. Okay, so uh, let me start by writing again the theorem by Shane and Uhlenbeck. Okay, so the theorem is the following. Let's take the dimension bigger than 3, and let's take a map which is H1 from a closed manifold into a closed manifold N, and which is a minimizing map. Then the singular set, which is the set where of points in M where U is discontinuous, is closed, of course. Is closed. Discrete if n is equal to 3, and with Hausdorff dimension, so let me call this set S, less than n minus 3 for dimension bigger than 4. And the regularity result is that U is smooth outside of this set. Okay? Okay, so what I would like to do is really proving this statement. Okay, so there are several things to prove. Okay, in the statement. So let me let me. So first, what you want to prove is that the map is smooth. Okay, outside of this set. Second, you want to prove the first kind of partial regularity result that you want to prove is the Hausdorff dimension n minus 2 of this set is 0, okay, which is just, and then you want to prove the Hausdorff bound, okay. Well, S, or yeah, is n minus 3 for n bigger than 4 and the discrete. Okay, so a finite, it's a discrete set of points, finite set of points for n equal to 3. Okay. Okay, so these are the steps. Okay, so what I alluded a little bit last time, or I mean, what I explained last time was how to get basically the first two steps of the proof, and I put completely under the rug the third one. So let me give a little bit more details on how to prove this type of statement. It actually gives a general strategy when you have variational problems on how to prove partial regularity. But in any case, the proof is never easy. Okay, there is no easy way to prove this statement. Okay, it's never an easy proof. Okay, all right. So let me come back to um, So let me start by the last lemma I explain. The first lemma that is actually crucial for several of the argument, and which is the monotonicity formula. So the monotonicity formula is the following. So let's take n bigger than 3. And okay, now I will take you always a map from an Euclidean ball, okay, because it's a local result. So there is no problem in assuming that there is no curvature in the domain for such a thing, and minimizing, of course. Then for any x in omega and any radius r far, bounded away from the boundary, 1 over r to the n minus 2 integrated in a ball of radius r at x of the energy of the map is non-decreasing. Sorry, is non-decreasing. Doesn't go to 0. Up, it's non-decreasing. Okay, in R. All right, and you have even more. Not only is non-decreasing, you know what is so if you call this the rescaled energy, I call it E of U in BR, or B capital R minus E of U in B little r. You know that this is bounded below by sum on the annulus of this quantity 2 minus n and the radial derivative of u squared. Okay, so not only you know that this is non-decreasing, but you know exactly what is the price you pay in the monotonicity. Okay, this is this factor. It will have like a very important consequence later. Okay. Okay, so the proof of that is by direct computation. Okay, so you kind of cook up like an easy competitor and then you do the computation. Okay, if you add like enough regularity somehow, you can assume that you compute it directly from the equation if you want. Okay, so there it's not a free boundary. It's not a hard monotonicity formula that you can find, for instance, in free boundary problems. Okay, it's a much more straightforward computation. So it has like a very quick consequence. And the consequence is that. So since this is a monotone quantity, it tells you in particular that under this assumption, the density of order n minus 2 of u at the point x is always finite. And what is this density? It's always defined, I should say. And what is its density? This is just the limit when r going to 0 of 1 over Rn minus 2 gradient u square in the ball of radius r x. Okay, so it's just because this quantity is a monotone. Okay, so it has a limit. Okay, so okay, so this is the first lemma. So let me now go to the second lemma, which is the main, the main regularity lemma, which is the small energy. So this is the following. Hmm. So under the same assumptions, okay, so there exists a constant epsilon naught, which is positive, and a small number such that for any map minimizing in a ball of radius 1, okay, satisfying that its energy is less than epsilon naught square. Okay, so under like a smallness assumption in the energy of the map, okay, then you have the following decay of the averages or the energy, if you want. Okay, gradient u square is less than 1/2 over b1 of gradient u square. Okay. So it tells you that if the energy in a ball of radius 1 is small enough, then in smaller balls, you have geometric control because it's geometric because theta naught is a small constant, okay? Constant close to 0, but less than 1/2, and here you have 1/2. So actually, whenever you have this type of bound, so let me give you right away a consequence is that this type of bound tells you that U is always Hyder in a ball of radius 1 R over 4 where R is less than 1. Okay, so this is an application. This is first an iteration and then an application of Moray embedding. Okay. So this is really the crucial lemma to prove regularity because it tells you that under this assumption of bounded energy, of small energy, I should say, because there exists an epsilon naught, so that if the energy is small, then you have geometric decay of the energy, of the rescaled, of the rescaled energy. So this is like under this assumption, you are C alpha, okay? And yeah, so basically, like, so this is an iteration plus an application of Moray embedding, and I mentioned already several times that once you have proof continuity, automatically it gives you C infinity. So continuity is a hard thing to prove. Okay, you can invoke regularity, elliptic regularity to prove C infinity. Okay? So let me explain how to prove this type of statement. So, so this is like, I'm going to be following mainly the argument by Shen and Uhlenbeck, the way it's written in the book of Lin and Wang, which is a good reference for harmonic maps and their heat flows, right? This is it's Fanghua Lin and Changyu Wang. Okay, so the idea is the following. You want to somehow you want to use at some point some elliptic regularity and somehow. And to do that, you need to find a way to transfer the smallness in energy. So here, like first, let me make a first remark is that we have minimizing maps, right? So then in particular, if you want to use the minimality property, you need to build competitors. So in particular, the minimality property will give you access always to energy inequalities, okay, of Cacciopoli type. And the second remark is that we have also monotonicity, okay, of the energy. What is the monotonicity giving you? The monotonicity is telling you whenever you control, okay, what is giving you, what is the consequence of the monotonicity? Is that whenever you control at radius 1, you control also for all the radii down to 0, okay? Of course, I mean, so this is a very strong, it doesn't give you decay, okay? But at least it gives you a control, an a priori control. Hmm? So this is like, so the energy, the monotonicity of the energy gives you that control at radius, control at r equal to 1 implies control for any r less than 1, right? This is exactly what the continuity, what monotonicity is giving. Okay, so how the starting point is the following. The starting point of the argument is comparing somehow comparing the map U that you don't know if it's small to a smooth if it's smooth to a smooth map. Okay. And how do you do that? You can do that if the energy is small enough. So how do you build a smooth map out of your given map? Well, you take a radial modifier, okay, and you build the following. Let me put R here of X, okay, which is the sum in B1 of phi, okay, of R. Okay, I will explain you what it is, but you do a fake, well, you do some sort of convolution, okay? So phi R will be just uh, yeah, so phi r will be just the rescaled modifier. Okay, so 1 over r phi, or 1 over r to the n, sorry, phi of r of x of, okay? So this way you build like a smooth function, okay? But of course, like it does not satisfy the constraint, so you cannot use it as a competitor, huh? However, for sure, it's a smooth function. It's a nice function, okay, because you are basically convolving. And but the thing is that there is a problem because when you want to use competitors, so when you want to use a minimality, you need to you need to kind of I mean, the principle of minimality is that the competitor has to have like H1 regularity, satisfies the constraint of being in the target N, okay? And for N, you can find the ball, okay, which is for which the competitor has the same boundary value as the minimizer U, okay? So this is what this means to be like a I mean admissible competitor, but this is not the case of the map here. Okay, this is not the case in general of this map. Okay, so first, we don't even know if this map would satisfy the constraint, okay? The fact that, I remind you that you have this constraint, right? You have like, oops, you have that, remind you that you have this constraint, right? That U is from B1 into N, okay? So in particular, U of X belongs to N almost everywhere, right? And so these are constraints that you have to check for every of your competitors, okay? So this is your admissible. Okay, but you can prove, and this is basically just a consequence of Poincaré inequality, that if the energy is small enough, you can prove that you can choose. Okay, so you can prove that one can find a R which actually depends on X, such that the map with this R of the ball of radius 1/2 is in a tubular neighborhood of the manifold N. So this means that this map, you can project it. Okay, so this means that if you take the projection from on the manifold, so from the tubular neighborhood into N, okay, so this is a projection here. Oh, sorry, the projection. And it's well defined if and only if you are like this, I mean, you belong to this tubular neighborhood. It tells you that then, because of the Poincaré inequality, your map here can be projected, and so you can build a new map. Okay, you can build so let me write it here like this. You can build a new map. Oops, sorry. Can build a new map, U of R of X, of X, if you want, which is just the projection, this projection of this map. Okay? And now, of course, it's a map. You can see it as a map from B1/2 into it. Okay? Okay? So this is the first step. Now, at the moment, the map didn't yet satisfy, is not yet a competitor, okay? You cannot use it completely. Okay, because the map has you don't know if it's going to satisfy I mean, it doesn't satisfy the boundary, so you need to change it to use it. I mean, you will not use it per se as a competitor, but you will use this map to build a competitor. Okay. Okay. Um, all right. So basically, once you have built this map, which is some sort of a good projection map, if you want. But once again, you cannot yet use the minimality property. However, this map is relatively explicit, huh? Right? I mean, this is just a convolution with a radial modifier, right? I mean, the convolution, you integrate in D1 a radial modifier, which is infinity, well chosen, okay? So you have to tweak it a little bit, but it's not. With this convolution of this smooth function, with your map U, okay? So the next step afterwards, if you want to prove really like the regularity, is building what is called and is always used in this type of thing, what is called the harmonic replacement of URX. Okay, so let me call this new map UH like this. Okay, And what is the harmonic replacement of something? The harmonic replacement is the solution to the following Dirichlet boundary problem. You construct an harmonic function in the ball of radius 1/2, which takes the value UH on the boundary. So this is the function V is called the harmonic replacement, okay? And UH here, well, the harmonic replacement of UH. Okay, so you basically solve the Dirichlet problem of being UH on the boundary of the ball of radius 1, and you fill it inside harmonically. Okay. But of course, like, what did you gain here? You don't know what, I mean, you know that UH is a nice function, right? Well, at least it's a function which has uh, bounded oscillation and somehow like satisfies some nice gradient inequalities in terms of the energy, though it's not your map. Okay? It's a modification of this map here. But what you gain here is that you know that V is much better than that because V is infinity, it's harmonic. So in particular, since it is harmonic, it is its gradient square is subharmonic, right? So it satisfies many good inequalities, okay? And the soup, for example, in a ball of radius 1/4 of gradient V square will be bounded by this, right? Well, there is a constant here probably. And this, okay, you can relate it to UH, that you can relate it to a constant times the energy in a ball of radius 1. And this is just because you can relate it to the boundary, to the value of V on the boundary. Okay, which is UH that you relate by the properties of the convolution. Okay, the gradient of UH. The gradient of UH, you can, because of the way it's here, you can relate it to the energy, okay? Just because of the definition. Okay. And U is smooth, right? UH is smooth, sorry. Okay. Okay, so once you have this this subharmonic function, this harmonic function V, you can use actually minimality to prove an energy estimate and to prove. So the whole point consists in use V to transfer regularity, but even more regularity, like estimates, decay estimates of the energy from V to UH and to U. Okay. Okay. So at some point, of course, like you will. I mean, at some point, one has to use, like the compete. I mean, the fact that you can build, you can adjust the radius h, because remember that the radius h is actually a radius, huh? Okay. I mean, you want to think of it as a radius, which can depend on x, but the thing is that you can adjust it so that it's going to be a correct competitor. Okay, so one of the points of Shane-Uhlenbeck that they notice is that you can use this modification, and by just adapting the radius because the estimates are like well behaved with respect to the radius here, to the r variable, by adapting the radius as a function of x. Okay, so adapting the radius in terms of the point where you look at your modification. So the point x, you manage to adjust it and to make it a competitor. Okay. So this is like the first, all of this work, which is several pages actually, because there are some non-obvious like energy estimates to develop. This is just to prove the epsilon regularity. Okay. So are there any questions or up to now? Okay. So this is as a almost a direct consequence of the epsilon regularity. So this last statement, by just some sort of covering argument, okay, you can prove that the singular set of the map is the set where the density is positive, and actually this is a set where the density is bigger than epsilon square, right? This is my epsilon regularity. And the n minus 2 Hausdorff measure of this set is 0. Okay, so this is really like the monotonicity. Okay, and so this type of statement is just monotonicity plus covering. Okay, so this follows by the monotonicity. Okay, this is to prove C alpha. Okay, plus covering. Okay, I mean the Vitali covering, the usual covering that you can find when you prove some boundiness. Okay. Okay, so now so what to do with the refined version? Okay, so the refined regularity of the singular set, refined bound on the singular set, because of course here this is just here what you just say is that the n minus 2 of Dorf measure of the set is 0. Okay. So you are not still, so it does not imply that the Hausdorff, what you want to prove really is that the Hausdorff dimension of the singular set is bounded from above by n minus. Okay. So, okay, so this is usually a hard thing, and the proof is based on two arguments to prove this bound, okay? So the first argument is that, the first lemma is the compactness of minimizers. Okay, so let me state it. There is no easy proof of this lemma either, by the way. So if you take a sequence UI of minimizers, of minimizing map, if UI is weakly converging to U in H1, then actually it's compact. So UI is strongly converging in H1, and U is a minimizer. Okay, so this lemma is crucial because it tells you that whenever you start with a sequence with minimizer, its limit will be a minimizer. This is very important. Okay. So there is no easy. I mean, there are several proof, and probably now the most handy proof is a very nice proof by Lukaus, which is a very clever interpolation argument. But there is no easy proof. It's not an easy result. And this is the features of minimizers. Huh? The limit of stationary points is not stationary. Okay. One doesn't know how to prove that says a statement. There is compactness of stationary maps. Okay. What you have is full compactness in H1 of minimizers. If you have a weakly converging limit, a sequence, then it's actually strongly converging, and the limit is a minimizer. Okay, so this is very important. Okay, and why is important? This is because you're going to use so the next result is if the limit is a minimizer, then you can use the monotonicity property, right? Okay, but because the monotonicity holds for minimizers. So if you take a sequence of minimizers, its limit is a minimizer, and in particular, its limit will satisfy the monotonicity, okay? But let's pick a special sequence of minimizers. Let's pick the sequence which is given by stretching your map by dilations or by rescalings, okay? So, because those maps are the candidates to produce for singularities, okay? Remember that we know already that a singularity, a map which is singular is x over mod x, okay? So this map is zero homogeneous, right? X over mod x. So if you take the map x over mod x, right? Which is a model, right? X over mod x, okay? So if you call that u of x, okay? So u of lambda x is equal to u of x for any lambda positive. So this tells you that u is zero homogeneous. And of course, this map, right, is from Rn into minus the origin into Sn minus 1. Okay? But you see, like this map is not localized, right? So this map is defined on the whole cone Rn minus the origin, right? So somehow this map is, and how do you imagine that, how would you get such a map? You would get such a map if you were taking somehow a limit, okay, of minimizing maps, uh, um, which are obtained by, so let me take this as a definition, okay? So clearly, 0 is a singular point, okay, of this map, all right? So what you would say, like, how would you define a point in the singular set, okay? So you would take a map from H, like N, okay, which is minimizing, and X naught would be a point in the singular set of U um, if somehow there exists okay, so you would attach to X naught a map. Let me write it this way. A map phi, which is also an H1 lock map, but this time in all of Rn, and it's called the tangent map if there exists a sequence of radii going to 0 such that your map, which is obtained by centering at x naught and rescaling as Ri, is weakly converging to such a map phi. I denoted it. Okay. So such a map phi is so weakly converging in H1, okay? Log of Rn. So really like x over mod, think about x over mod x somehow. You want to look like more and more like x over mod x, okay? Well, you don't know if the map will be x over mod x, okay? But of course, like if x naught would be if x naught would be a singular point, phi would be, if x naught is the origin, if you want, phi should be x over mod x, right? Somehow, okay? So I'm just trying to define it. So why do I do that? So these maps phi are called tangent maps, and they are like the elements which describe globally your singular set. Okay, they come from rescaling maps. I mean, dilating maps. Sorry, in X, dilating maps around a singular point. Okay. Um, and they are defined, okay, so what you want to understand are those singular maps, okay, those tangent maps, okay, those singular maps, right? If you understand those, you understand what are the singular points. Okay. Well, okay, so this argument I should mention comes from Federer in GMT, when Federer designed arguments like based on that when he studied area minimizing currents. Okay, so it's like originally this type of argument comes from minimal surfaces. Okay, the fact of understanding tangent maps. Okay. Okay, so I'm not yet done in the sense that I just defined the object, which would be the candidate to describe my singular set, but yet I'm not still at the level of the dimension bound. But I used something very important, is scaling, right? The thing which is coming with a tangent map is a sequence of radii. So you are really zooming, okay, at the around a singular point x naught, okay. So what Federer design is a way to classify the singularities and to classify the singularities and in terms of the symmetry of the tangent maps. And so the whole point of the dimension bound is to introduce a stratification in the topological sense of the singular set U, which is, so you introduce a stratification, which is, so you introduce a stratification, so a bunch of open manifolds, which such that each stratum is so a set of points in the singular set of the map, such that the dimension somehow of the invariant space of the tangent map phi is less than J for all the tangent maps at U. Okay, so it's a little bit, it's very it's technical to explain, but what Federer understood is that what describes the best the singularity as the spaces, as the subspaces which are left invariant under the subspaces which leave invariant these tangent maps. Okay, so you pick yourself a point in the set, on the singular set, you blow it up by rescaling this way, you get a tangent map. Then it's not very hard to prove that the tangent map or the singular set of the tangent map, I should say, is a place where the tangent map is invariant, has some invariance, okay? And using that, so the dimensions, the various dimensions of these invariant spaces, you can prove that your singular set admits the following stratification. So there is a filtered, a nested so all of these sets are nested, and the singular set, which is the singular strata, is the one which should have the dimension at most n minus 3. So this would mean that this you see, this invariant space has of the tangent map has a dimension at most n minus 3. And then the lemma, okay, which is called the dimension reduction of Federer, is telling that for any of the J's, the Hausdorff dimension of the singular strata is J. And from there, you get the dimension bound. Okay, so the idea of the proof is really based on first the epsilon regularity. This is the important. I mean, this is the first important theorem to prove. Okay, the epsilon regularity, and the second one is the Federer dimension reduction. But and really, like, I didn't give. I mean, I gave more detail and explained like the proof. I mean, the strategy, but filling all the details is not an easy task at all. It takes several pages. Okay. So yeah, so this is basically like the way you prove Shane-Uhlenbeck theory. Are there any questions or on this part? So let me make a remark. Like this this statement, this dimension reduction à la Federer does not work for stationary map. Okay, I remind you, like a stationary map is a map which is stationary for domain variations. And so you take like a family of one parameter family of diffeomorphisms, and you compose your map with those, okay? And you take the Frechet derivative of the energy of such maps, and you take it at t equal to 0. These are stationary maps, and a map is stationary if it satisfies this criticality assumption. And the thing is that the limit of stationary are not stationary. And so basically, and the fact that limit of minimizers are minimizers is also very important. Let me mention that again, because I alluded it, but then I forgot to mention it. Why it's important that the sequence of minimizers are minimizers? Let's look at the monotonicity formula. Okay, so let's look at the monotonicity formula. What is the monotonicity formula telling me? The monotonicity formula tells me that, okay, the deficit, right? So the difference in energies is actually measured by the radial derivative, or even like a special radial derivative of the, right? Because there is this weight here, x minus y to the 2 minus n of the map U. So when you take a sequence of radii going to 0 exactly when you look at your tangent map, and you take the limit in the energy inequality, it tells you that the tangent map, okay, has to be zero homogeneous. This is exactly what like the energy inequality tells you, and this is exactly what the map is telling you of the difference, the monotonicity, right? Because if this term is vanishing, this means that you are zero homogeneous. Okay. So somehow, like this is really like the monotonicity. Okay. So the monotonicity is telling you that you are. So the monotonicity is telling you that you are zero homogeneous. So all the tangent maps are zero homogeneous. So they all look like locally as x over mod x, if you want, which is somehow like the model map for your singularity. Okay, so it's very important here that limits of minimizer are minimizers because you want to pass to the limit in the monotonicity. The thing is that stationary map satisfies the monotonicity. Okay, it's been known for a long time. However, limits of stationary are not stationary necessarily, and so you cannot use this dimension reduction of a la Federer that I just mentioned. Okay? Okay, so okay, so this like basically gives general approach for partial regularity and really the Shane-Uhlenbeck theory. All right, so let me come back now to what I described last time, which were this harmonic map with free boundary. Okay. Okay, so let me start and let me remind you what are harmonic maps with free boundary. And so I will just introduce now what I will talk about next time, so tomorrow. So basically now you consider the same energy as before, except that your map is from M into N, and you add a constraint that it maps the boundary of the domain into a submanifold of the target. Okay? And what I tried to convince you last time is that when you write Euler-Lagrange equation of that, okay, then you get your favorite harmonic map system, okay, when on M, but this Neumann, nonlinear Neumann condition. Okay. So of course, like now, really like if you do like a picture, draw a picture, you have like, imagine that B is like M is a ball, okay? So you have a ball, you send it to a manifold N, okay? But the boundary of the ball, which would be the sphere, okay, is sent, okay, it's mapped into this sigma here, which is a closed submanifold of N. So of course, like when you look at my system here, somehow, like as far as the regularity is concerned, there would be two issues, right? The interior regularity, and now you have really a boundary. Okay, so the boundary regularity, and since this is not a Dirichlet problem, okay, so it makes sense even more here to look at boundary regularity. And what so this is really the new thing to investigate in this type of maps, okay, is of course, and this is what I will describe in more detail next time, the existence and the regularity. And as far as the regularity is concerned, what we would be interested in only is the boundary regularity. And so taking what I tried to describe last time is that taking N to be Euclidean, then somehow your problem boils down to something which is of this type, and U, for instance, du d nu, okay, would be orthogonal to sigma, and think about sigma to be like a sphere. Okay, let's write it this way, like a sphere. It's going to be easier to understand, to see. A minus 1 of U, okay? But of course, here, this is on the boundary of M, okay? And, okay, so now the whole point is that you introduce the Dirichlet to Neumann map of U, which is, by definition, the new U, okay, whenever, okay, U is, so this is just the Neumann trace of U. And what you can prove is that if M is a half plane, so let me have space, sorry, this directly to Neumann map is from H1 half of Rn, which is seen as the boundary of into H minus 1 half of Rn, and it is exactly equal to the Laplacian, and here is the Lap of the trace. And here this is the Laplacian in Rn. Okay? So, using that, if I use the fact that the Laplacian 1 half comes as the Euler-Lagrange equation of H1 half semi-norm. Actually, what I showed is that harmonic maps with free boundary appears as harmonic extensions of half harmonic maps, which are just the maps obtained by taking as an energy the Gallardo semi-norm and with the target of being Sk minus 1, almost everywhere in X. And if you use a Gallardo representation of such maps, you get that half harmonic maps. So here my U, okay, is a trace of U being here, okay? I call it the same, but this is a trace, okay? U is seen as a trace here, okay? Trace on the Rn, okay? So trace on the boundary of the domain. So when I use that, I can get, so it might be useful, this type. Maybe it was written in the case of the circle, but it works for any, sorry, it's 1 here. It works on any dimension for the domain, for the target, sorry. And here, U of X. Okay, and this term here, this term here is really like a gradient, right? This is, or half gradient, I should say. It's really like the square of a half gradient. Okay? So somehow there is like some sort of dictionary, right? So this is interesting thing. There is some sort of dictionary between harmonic maps with free boundaries, or at least a class of harmonic map with free boundary, those which are obtained by extending harmonically inside in a linear way, I should say. Those harmonic maps with free boundary, and these half harmonic maps which have been introduced by Dalio and Rivière. Okay? But then it gives somehow two viewpoints. Either you see on this class, special class of harmonic map with free boundary, everything boils down to understand much better the boundary behavior. So when you have in mind this, that, everything boils down to understand better this equation. Okay, this is what you want really to address. Okay, but then you okay, so but somehow the geometry of a harmonic map with free boundary is pretty complicated because you have somehow this interplay between these three spaces, right? Because originally your full problem involves, I mean, these three manifolds, M, N, and sigma, okay? So here I got rid of one of them, N, which is assumed to be Euclidean. But somehow this computation still works, but there are error terms when you put, whenever like you really take M, N, sorry, this target to be, let me show it. When you really take, you don't take N to be Euclidean. So the computation I just did still works somehow, at least I made principal order, except that they're going to be all the additional terms, the commutation terms somehow coming from the fact that if N is not Euclidean, you have really nonlinearities inside as well. But one can still, at least to some extent, give some regularity result when one looks at this type of problem. Okay, so what I will describe last time, and let me finish by that. What I will describe last time is, next time, sorry, is basically two flows which are like candidates to flow harmonic maps with free boundary. So you ask yourself the same problem as the homotopy problem. You want to deform a map, and so you want to design a flow to do that. And so the first one would be really like the map, this flow, which would be a very from on M, and the nu equal, well, orthogonal, I should say, to the tangent at sigma. So this is the flow one, and this is a nice flow. Okay? But there is another one. Instead of flowing with a like nonlinear Neumann boundary condition, let's flow directly on the boundary, right? So the other flow would be dtu plus, but then on the boundary, you don't flow the Laplacian, you flow the half Laplacian. And you want to flow this equation, right? So this is the distribution. And here, u, okay, is not the same u here. This u here, okay, let me call it u tilde. This u tilde is defined on the boundary. Okay? So these are two flows which are candidate to flow for flows for harmonic map with free boundary. Okay? One is directly considering a caloric extension, and the second one is looking at the formulation as a half harmonic map, and then, of course, building an harmonic extension. But we will see that these two flows are very different and analytically exhibit very different properties. And this is what I would like to discuss next time. So, yeah, so I think I'm going to stop here for now.
Okay, any questions? Yeah.
Professor, just a clarification of two notations from the main proof you wrote, where you were trying to define this radial modifier, PR. So the integral, you wrote it as VR of x minus y. So do we have to view it in terms of the exponential map by taking a pullback?
Oh, yeah. But remember that I'm always working on the Euclidean patch for the domain.
Okay.
If you are doing, okay, you're correct, of course. If you are looking at all this, since I was only looking at regularity issues, right? If you are a smooth manifold, like you just have like terms which are smooth, so you can, without loss of generality, for regularity, you can consider that the domain is a smooth ball or smooth domain if you want. So I don't need to do the exponential map. If I were looking directly on a manifold, yeah, I would need to introduce an exponential map. But if I want to build the same type of smooth map, but here I was looking at a regularity issue, so I
this
put
will be
myself.
like we can take like the normal balls in the case of manifolds because we are doing locally. Okay.
Yeah, because everything is local. Yeah.
And there was a notation of U subscript R and U superscript R, where you were able to show U R of x of ball of radius half is contained in n delta naught. So this n delta naught, you are viewing it as like a Catalogus neighborhood in the codomain, or?
Yeah, no, yes, it's a tubular neighborhood in the codomain in N, yes. Because like when you define a projection, okay, so you have to always to satisfy this constraint of being in the target, right? So the best thing would be like, let me deform the map a little bit, and then project it on the manifold N, so that I'm sure that the constraint will be satisfied. But this projection is well defined if and only if you are close enough already of the manifold. But if the energy is small enough, this smooth map that I built if the energy is small enough, you can prove by just a Poincaré inequality that this smooth map will be close enough to close enough to n, will belong to the tubular neighborhood of n, for which the projection map is well defined. And
Okay.
so then you can project this map. You take this map and you project it.
Okay. And just one more clarification on the definition of in the definition where you consider this tangent maps, this phi. So before that, you motivated with the example of x mod x by x quotient mod x. So
Yes.
is it like we are trying to view the minimizer as locally modeled as x by mod x near the cone, where you had this two subbelow space defined? One is you took in h1 omega n, but you try to approximate it, or in the limiting case, it was lying in h1 log of rn comma n. This tangent map phi. So you define this u of x naught plus rix convergent weakly convergent phi.
Yeah.
So is like what can I always like try to imagine phi as x my mod x, or are there?
No, I mean it's just in the case. It's just that this only explicit map that we have whenever the target is a sphere, right? Because if
Okay.
you are on a general target.
Okay. So that is like the model case when you have n to be like sphere.
Yeah. That's a model case. But this is good enough somehow. It gives you enough insight to understand, because as I mentioned many times, like whenever you are looking at regularity result, I mean, the closed case, smooth, it's like a sphere. You can assume to be the sphere, and it's good. It will give you like all the same results and so on. So it's enough to think about this. You are not losing too much by thinking this way.
Okay. Thank you. Thank you very much, Professor.
Sir, when you were describing stratification of the singular set, you had mentioned something about the invariance of tangent maps. Can you please briefly recall what you just said over there?
Yeah. So let me state. Let me state actually like a proposition that I didn't state, but which might like clarify what I meant by that. So let me collect properties of the tangent maps, okay, in the sense that I defined it before. So let's take a minimizing map, okay? So this is a minimizer of your problem. Let's take phi to be an H1 lock, okay, of Rn into n, okay? So this is your tangent map. And it's a tangent map at x naught, which is a point of the singular set, okay? So you are not, point where you are not continuous. So then you can prove the following thing, okay? First is that the tangent map is a minimizer, okay? I said that already. And it's zero homogeneous, okay? This is for the zero homogeneity follows from the zero homogeneity follows from the monotonicity formula, and the minimality follows from compactness of minimizers, okay? And the second property that you can prove is that this space, okay, the point in Rn such that the density, okay, of the tangent map is independent somehow of the point, okay? This space is a linear space, okay? So this is a statement, a linear subspace of Rn, and phi, the tangent map, is invariant. Phi is invariant. You can, under translations, so composition with translations, I mean, by elements of this space. By elements of SF phi. So this is actually the property that you use for the stratification.
Hello.
Yeah.
So I have two questions. The first one is, so you defined minimizing harmonic maps, and you remarked that the singular sets for minimizing harmonic maps have codimension 3.
Mm-hmm.
So do we have better notion of weak harmonic maps, as in which have higher codimension?
Yes. Okay, so it's okay. So by the argument of Rivière, okay, by the counterexample of Rivière, by the example of Rivière, weak harmonic maps cannot be weak in the sense of weak solutions in the H1 sense, okay, solution of the distributional equation. And we know that there is no regularity at all. They are discontinuous everywhere. There is one case where you can define weak harmonic maps, even in dimension 2, for which you would have a singularity. I remind you that, so this is like, I don't know if I answer your question, but okay, so there is another notion of weak harmonic map, which are stationary maps, right? Stationary maps, so then stationary maps, I mentioned that before, are maps which are satisfying this criticality t equal to 0 condition, and phi of t is the one-parameter family of diffeomorphism close to the identity. Okay? So for those, actually, there is no dimension reduction in the sense that I define. You cannot argue this way. There is a very hard, very complicated paper of Lin where you can, it's an annals paper, where you can define some notion of stratification, but not in the way I defined it for such maps. Okay? Now let me make another remark. This is what I was starting with, is that in dimension 2, okay, we know that weak harmonic maps, weak in the same H1, okay, are smooth, but actually you can define the notion of very weak harmonic map, for which like actually you are not smooth even in 2D. And those are maps satisfying an equation of this type. So you see, like, if you are smooth enough, this is, so if you are H1, this equation gives you, if you are H1, like the weak equation of harmonic maps. Here I wrote it only for when the target is a sphere. But if you start with this equation, if you are not H1, if you are below H1, okay, you can start with this equation instead of very weak, and then it wouldn't be smooth. A solution of that would be, actually x over mod x is a solution of this equation in dimension 2, but is not a weak harmonic map in the H1 in dimension 2.
Okay, so this is interesting, but I was actually asking for a better formulation, which has, I mean, a notion of weak harmonic maps whose singular sets would have higher codimensions than 3.
So yeah, so you would mean like dimension n minus 4 and okay, or things like that.
Yes.
No, I'm not aware of this type of thing for maps.
Okay, so
There are, like,
minimizing is
there are geometric objects having codimension 4 bounds for singular sets, but these are not maps. These are Yang-Mills connections.
I see.
Okay,
Oh.
so if you so maybe like it's so if you want, so I don't know any notion of map leading to weak maps having codimension 4 bounds. But if you look at somehow sections of connection, okay, so if you look at maps coming from section of connections so on vector bundles, then it would have codimension 4 bounds.
I see.
I don't know. Yeah, because you can, yeah. But you have to, yeah, the only codimension 4 bounds that I know are like, don't know any. I mean, yeah, it's not clear how to define the notion of weak solution for maps, at least to me now, like for codimension 4. For connections, if you are looking at connection, Yang-Mills connections, so some of them coming from like the Yang-Mills curvature, then you can define, then you're going to have codimension 4 bounds. But this is another this is related to harmonic maps, but it's geometrically it's different.
I see. Also, are every smooth harmonic map minimizing?
Do you mean like explicit ones, or
Any general smooth harmonic map? C infinity.
yeah, but you mean like explicit ones? I mean, like, or because there are like some there are some examples. For example, there are some you can build maps into the two sphere or the 3 sphere, which are smooth everywhere and minimizing.
But are there smooth harmonic maps which are not minimizing?
Oh, which are not minimizing? So then if they are not minimizing, okay, you would like them to be stationary. These are very difficult things to imagine. I don't have any example on the top of my head like this, but yeah, like I'm not sure.
Okay, thank you.
See you tomorrow. Thanks. Bye. Have a nice day.